So yeah, so we start with the definition. Uh, so you know, so given a graph G, suppose you have an edge whose removal uh, increases the number of components of the graph. So such edges are called cut edges, because if you just remove one edge, it disconnects the graph. So this tells something about the uh, the graph, that it is its connection. So we have defined what's what does it mean for a graph to be connected. But now we can ask how well the graph is connected, and then you can we will come later to see what does it mean to say that a graph is highly connected, or the connection is very weak. So such things we can do, and one of the first directions is to see that if you have some edge which if you remove, the graph becomes the connectivity is low, that the number of components increases. So if you start with a connected graph, you can say that okay, after removing an edge, it becomes disconnected, which means that there is a weak link, right, in some sense. Like if you are representing your graph for say a communication network, then there is some connection. If you remove your entire this thing becomes disrupted because there is some disconnection. Or like if you have military network, there are some weak points like bridges. If you remove one of these bridges, then this military from one side cannot reach the other part, right? So such situations we want to avoid, maybe, right? And for such things we will denote such edges, for example, by a cut edge. So a cut edge is basically, here is an example, right? You have a graph, maybe, right? You have an edge, and if you remove this edge, let's say E, right, equal to xy, and then you will see that if you remove that edge, then the graph loses its connectivity, right? It becomes disconnected. So these are called cut edges. Sometimes it is also called bridges. Okay, so cut edges are also known as bridges. So in some textbooks, you will see bridges more often. So yeah, so even if your graph is initially not connected, you can still define cut edge, because if it increases the number of components, then it's a cut edge, right? So here is a cut edge, right? Here is another cut edge. So such edges are called cut edges. Now, if you remove an edge, it cannot increase the number of components by more than one, right? Because if you an edge only connects two vertices, so either it disrupts the connection between those two, or it doesn't, right? For example, the other edges in this graph are not cut edges, right? So this edge is not a cut edge, because even if I remove this, the graph remains connected. I mean, the part of the graph, the component remains connected. So, if after removing an edge, the number of components may change or may not change, right? If it changes by exactly one. Otherwise, it doesn't change. Okay. Now, given an edge that is a cut edge, right? One can say that it's a cut edge if and only if it does not belong to any cycle of the graph. And this is kind of intuitively clear. Why, right? Because if it is part of a cycle, you can visualize that, removing that will not disconnect. And if it is not part of any cycle, one should be able to see that it actually disconnects, right? So if E is equal to xy is some edge, right? Then for example, right, like here, right? This is a cut edge, and then if you see that it is a cut edge, you can verify. First of all, you can verify that it is not part of a cycle, right? And you take any other edge which is part of a cycle, you will see that it is not a cut edge. Now, how do you prove this formally? So to formally prove this, we can do the following. First thing is that you can assume that the edge is a cut edge. Now, what happens if you remove the edge, right? So if you have a cut edge and you remove the edge, okay, sorry. If you have a cut edge and you remove the edge, then by definition, right, the endpoints x and y, right, now belongs to different components. So after removing the edge, this component has become two components, which means that between x and y there is no path in the graph, right? So after removing the edge e in g minus e, there is no xy path. Now, if there is no xy path, right, uh, e could not have been part of a cycle, because if e was a part of a cycle, then after removing edge there is still another path, because by definition cycle is basically you have a path and then you have an edge which connects the endpoints of the path, right? So so therefore, if e is not a cut edge, it cannot be part of a cycle. On the other hand, suppose e is not a cut edge, right? If e is not a cut edge, then you take an edge which is not a cut edge. For example, here, right? The E, which is not a cut edge. Right? Now, after removing the edge, because it is not a cut edge, after removing the edge, x and y still belong to the same component, right? Maybe another color. X and y belongs to the same component after removing the edge xy. So which means that there is some xy path, right? Because a graph is connected, then you know that between any pair of vertices there is a path, right? So you take any path from x to y in g minus e, right? Now take this path, let us say p, right? And if you have this path p, and then you add the edge xy to it, right? Then p plus xy is a cycle by definition of a cycle. Right? So therefore, the graph contains a cycle. So this is the proof. You can formally write it as follows, right? So if E is a cut edge of G, then X and Y belong to different components of G minus E, and if there is a there cannot be a path between X and Y, right? So there is no path in X and Y between the endpoints, right, which is X and Y of the edge. Therefore, E cannot be part of any cycle of G, right? And conversely, if E is equal to xy is not a cut edge, then x and y belong to the same component, and therefore it has a path, xy path, let's say p in G minus E. Now you add back the edge E, right? So therefore p plus E forms a cycle, and this cycle is a subgraph of G. So therefore E is part of, and it contains E, right? So that is the proof. Okay. Now, similar to cut edge, you can also talk about cut vertices. A cut vertex is basically a vertex whose removal increases the number of components. Now, on the case of cut edge, you saw that the number of components can only change by one, right? Uh, but with respect to cut vertex, it may not be the case. You can have, depending on the degree and the type of the graph that you are looking at, the number of components can increase by more than one. So we can only say that it is strictly larger. Right? So if x is a cut vertex, then the number of components c of g minus x is strictly larger than the number of components c of g. And then in such case we say x is a cut vertex of g. So here is an example. You have this graph and you have several cut vertices. So maybe you can try to see which are the cut vertices. So this is a cut vertex, for example, right? Because if you remove just this vertex, you have the remaining parts, this and this, right? So they will be two different components, and the number of components increases, right? Similarly, vertex is also a cut vertex, the same idea. This one, this one, right? Each of these, if you remove, the number of components increases by one, right? On the other hand, if you remove this vertex, it increases the number of components by 2, right? You will have 3 remaining components because this part becomes one component, becomes another, and this becomes another, right? So, yeah. Now, if a graph has a cut vertex, then the graph is said to be separable. Okay? And if there is no cut vertex in a graph, then it is non-separable. So, this graph was a separable graph. But if you look at a graph with no cut vertex, right, something like this, then it is a non-separable graph. So non-separable in the sense that just by removing one vertex, you won't be able to separate the vertex into two parts, disconnected two components. Okay. Now, a covering. So we already discussed what is called decomposition of a graph. So decomposition of a graph is basically a list of subgraphs where every edge appears exactly once in this list, right? So every subgraph basically it's a partition of the edges, right? So decomposition is basically a collection of subgraphs which forms a partition of the edges that every edge appears exactly once. On the other hand, a covering is saying that okay, every edge must appear at least once. Okay? So a covering of a graph is a family of subgraphs such that each edge appears at least once, and that means that the union of overall the subgraphs in the family must be equal to the edge set of. So that is all, right? So if you uh, so there is so if you look at this cycle, right? So this is one cycle, and look at this is another cycle. So I have two cycles now, right? So let's say 1, 2, 3, 4, 5. Right? So 1, 2, 3 cycle, and 2, 3, 4, 5 cycle, right? So these two cycles are subgraphs of the graph, and it forms a cover because all the edges appear at least once, and the edge 2, 3 appears more than once, and others appear only once. So that is okay, right? So it is still a covering. You can talk about coverings of different types of graphs. You can say a covering of the cycles. So that's called a cycle cover, right? You can talk about covering by some other type of subgraph that you want. So each different types of path cover, you can talk about path cover. Let us look at a path cover. How do we do that? Right? You can look at, say, this is a path, right? One path. Then you have another path. And you have another path, right? Or if you want, you can even put a dark path like this. So either way, they form, this subgraph form a path cover. So one can talk about different sides. And a covering where, is a k covering if every edge is covered exactly k times. So if all the edges are covered, exactly the same number of times, it's basically a uniform covering. And if it is exactly k times, it's a k uniform covering. And such k uniform coverings are just called k coverings. So a k covering is basically every edge appears exactly k times in the subgraphs. Now, if it is a one covering, it is basically a decomposition, right? Because every edge appears exactly once in the in the covering. That is the definition of decomposition. Now, a two covering, right? Every edge appears exactly twice is called a double cover. Just just a name that is represent that it is two covering. And if you have like if you have that every member of a covering family is a, yeah, I already defined this, right? Is a path, it's a path cover. And if it's a cycle, then it's called a cycle cover. Yeah, so cycle covers, we already know something about cycle covers, right? We already saw that if a graph, every vertex of a graph has even degree, then we said that each component is basically Eulerian, that it has an Eulerian tour, right? And Eulerian tour is basically a closed tour. And then we saw that when we prove that a graph is Eulerian, then we actually proved that, and even if it is Eulerian, then we actually proved that it has a decomposition into cycles, right? That is how we, in fact, our proof basically used the decomposition to come up with the Eulerian tour, right? And so therefore we saw that Veblen's theorem was a corollary to our proof. And hence we know that if the graph is even, that is all the vertices have the same degree, then uh, it has a cycle cover, right? Every edge appears exactly once because it's a decomposition. So it has a cycle cover. And if it has a cycle cover, then we know that it is even, right? That every vertex has even degree. Now, if there is a cut edge, of course, cut edges cannot be part of any cycle, so there cannot be a cycle cover if there is a cut edge in the graph. Now, one can ask, okay, if there is no cut edge, then can you have cycle covers, right? Now, you cannot have a cycle decomposition because we know that cycle decomposition exists only for even graphs. That is our proof, right? So it's an if and Veblen's theorem is basically an if and only if condition. Now, therefore, you can talk about let's say covers where the edges appear more than once. But now you can ask, okay, like because if every there is no cut edge, you can always every edge is part of some cycle, so you will definitely have some cycle cover, right? Not not a decomposition, but there will be a cycle cover. But now can I say that there is a uniform cycle cover, right? So one of the most famous conjectures, still open conjectures in graph theory is that does a graph without cut edges have a cycle cover where every edge is covered exactly two times? So that is called cycle double cover. Okay. So cycle double cover is a, a cover, a cycle cover of G where every edge appears exactly. Now one can ask, when does a graph have cycle double cover of or if all the graphs have? So the question is that if there is no cut edge, then no cut edge, does it imply, right, a double cover, right? Cycle double cover. Now can you think of at least some classes of graphs where there is a cycle double cover? If you think about a little bit, if you know that we already very briefly mentioned what are called planar graphs. So suppose there is a planar graph without cut edges. Okay, so now planar graph without cut edges means that there is a planar plane embedding of this graph. Okay, let's take a simple example like You remember this cube graph, right? So the cube graph is actually, so all the platonic solids have this, its skeleton basically forms a graph, and then you have, all of them are basically planar because, the skeleton, if you embed it on a sphere, remove one point of the sphere, you can spread it out, and then you get an embedding on the plane. So, so you have this, cube which is represented like this, and now you can see that this any such embedding, right? If the planar graph does not have a cut vertex, every edge is part of a cycle, and then all the facial cycles. Look at the faces of the graph. The face boundaries are cycles, and you can see that, and one can verify that. And if you take the list, if the collection of all these facial cycles, these cycles, right? All the faces are cycles, right? And will cover all the edges, and all the edges will be covered exactly 2 times because every edge is incident to exactly 2 faces. So the facial cycles will give a decomposition, which is a double cover, not a decomposition, will a cover, which is a double cover, right? So every edge appears exactly twice, and therefore that is the that's proof. So every planar graph without cut edges will have such a double cover. Then we can ask, okay, is it true for other types of graphs, right? Now, if you think about this, you will see that, suppose you can embed the graph maybe not on the plane but on other surfaces like higher genus surfaces like torus or other surfaces, such that every boundary of every face is basically a cycle. In that case, you immediately get a cycle double cover, right? Because you just do the same thing, right? Doesn't matter whether it is a plane or not. You just need to make sure that the face boundaries are cycles. So in that case, you can just use the face boundaries, and that will give you a cycle double cover. So any graph, we know that is embeddable on a surface of a large enough genus. But the problem is that we don't know whether there is an embedding where the where the cycle, the boundaries of phases are all cycles. So if that is true, of course, cycle double cover conjecture is also true. So therefore, these two conjectures are still open. Okay. Cycle double cover conjecture says that every graph without cut edges has a cycle double cover, and this is still open. And if any one of you is interested, you can take a look at this literature. 2 years or 3 years back, there was a very serious attempt to prove this by Mary Radcliffe, if I remember correctly, and her paper is appearing in the in the archive, math archive. But it has a bug. So somebody pointed out there is a bug in one of the cases, and this bug has not been resolved yet. So one can also try to see if there is a way to fix the bug. May not be easy. I wouldn't think it is easy, but so many people have worked on this. But it's a nice question, and you can try to see what you can do or how much you can, try to show something larger than this. If you can, prove some progress you can make, that is also very nice. So a good question for any enthusiastic people to think about. And as I mentioned, this conjecture follows if you have the other conjecture. I don't know whether I have marked its name. Maybe not. I don't remember though. That if I can show that any graph without cut edges can be embedded on a surface where the face boundaries are cycles. So that is another conjecture. Okay, that any graph without cut edges can be embedded such that all the face boundaries are cycles is called another conjecture. I forgot the name. I can mention in the next class. Then also this result follows. So that is another conjecture. You can also try to prove that. Okay, some questions, some homework questions before we proceed further. So let Qk be the simple graph whose vertices are the binary strings of length k. Okay? And then we say that, okay, the adjacency in this graph is that if you have two strings and the corresponding strings differ in exactly one position, then they are adjacent. This is called Hamming distance or something like that, I remember. Now, if you find the number of edges in this graph, that is one question, that can you find this? And then find the degrees of the vertices. And finally, for what values of k, this graph is bipartite. Okay, so you can try to answer these three. Here is another question, that is to count the number of 6 cycles in this graph that is drawn below. Okay, and we have to give a proof, of course. If you say that, okay, there are 20 cycles or 15 cycles, that is not a proof for me. I mean, right? You have to just give a reasoning also. Answer becoming correct is not sufficient. Now, as a hint, you can try to see, at least find one 6 cycle and then try to draw the graph, redraw the graph with this 6 cycle that is becoming prominent. Then you will be able to get an immediate proof, I believe, right? So if you can try to find another, so sometimes, this is a nice thing to play with graphs, right? You take a graph, try to redraw it, you will see some properties that were not immediately clear to you earlier. So this is one of the reasons why people like to look at graphs and graph embeddings, graph drawings, and things like that. There are branches of graph theory just dealing with graph embeddings and graph drawings, because that helps in many ways, not just by visual these things, but on many other presentations and many other questions. It is important. Okay, then there is another question that you have a graph which has m edges, then show that this graph contains a subgraph with at least m by 2 edges, which is bipartite. So a large enough subgraph which is bipartite. And the next question is to show with reasoning, right? That you cannot just say that it's not possible or it's possible, but you have to give a reason whether it is possible and if it is not possible. So if possible, draw a 5 regular graph. All vertices have degree equal to 5 with a cut edge, and then a 6 regular graph with 2 cut edges. So in either case, you have to give a reason. And finally, you have how many cycles of length n can you find in the complete graph K? And define. So here we define the average degree of a graph as the sum over all the vertices, the degree divided by the number of vertices. Then prove or disprove the following two statements: that deleting a vertex of maximum degree cannot increase the average degree, and deleting a vertex of minimum degree cannot decrease the average degree. So these two statements, can you either prove or disprove? Okay, we will go to the next session, next part. And before that, are there any questions? Okay. So every non-separable graph can be embedded on some surface such that the phase boundaries are cycles of the graph. So this is the circular embedding conjecture. And if this is true, of course, the previous conjecture, that is the cycle double cover conjecture, is true. Because if there is no cut vertex, then there cannot be cut edge also, right? Because if there is a cut edge, its endpoints are basically cut vertices of the graph, no matter what graph you are talking about, right? So if an edge is a cut edge, then its endpoints are cut vertices. So no cut vertex implies no cut edge also. So when we say that non-separable means that there is no cut vertex also. So we don't allow these kind of things, right? Vertices are not allowed. Right? So yeah, because in this case, so there will be some technical issues. We will see that when we discuss planar graphs. We'll come to that. Okay, so now we talk about acyclic graphs. A graph is said to be acyclic if it has no cycles, right? And it's a natural way to think about it, right? Now, acyclic graphs are also called forests, and we will see why. So, because if you look at an acyclic graph which is connected, then connected acyclic graph is called a tree, and uh, then you will see that immediately that the components of forest are basically trees, right? So trees are, the forests are made up of several trees, and therefore this is an analogy. So a connected acyclic graph is a tree. Now we can look at several examples, right? So each of each of the components here are trees, and therefore the entire thing forms a forest. Okay. So here is a tree, right? And here is a tree you are familiar with, right? It's basically a path. Path graphs are also trees, right? And then here is another tree which has this nice structure, right? There is one central vertex and all the other vertices are neighbors to it. So such trees are called stars. Okay. Then this is a particular star which is a complete bipartite graph on one vertex and three vertices, K1, 3. And this graph is called a claw. Okay? It has a name, claw. Then the other graphs, some of them has nice names. For example, we will come to this maybe sometime. That this kind of a tree is called a caterpillar. Now, what is the defining property of such trees, caterpillars? That if you suppose you remove all the vertices of degree 1, what remains must be a path. So, if such graphs remove all these degree 1 vertices, what remains is a path, then that is called a caterpillar. You'll see why. You can see why by the drawing itself, right? Why it looks like a caterpillar. Imagination, of course, imagination is required. And this is not the perfect drawing to see why it is called this name. This, if you remove the leaves of this, then what remains will be a caterpillar. So such graphs are called lobsters. Okay. Now I want you to come up with a nice drawing such that it looks like a lobster. So these are like imaginations of people, and yeah. So just mention this name because these names are quite commonly used in graph theory terminology, right? And there are several conjectures, which uses this terminology. So it may be useful. So this is a star. Star will be much more common. This is caterpillar, and this is a claw, and this is a double star. This has no particular name. That's it. So okay. So these are the examples, and the entire thing is a forest. This is a single vertex. This is a trivial tree, and so here are some nice propositions. Okay, the first proposition is that given a tree, any two vertex x and y are connected by a unique path, and we usually denote this by x ty because if the tree is t, x and y there is a unique path. So x ty says that okay, the unique path from x to y in this tree. Now, why is this unique path there? Right? Why the path is unique? I think maybe it's so simple to see why. I don't want to discuss the proof here. It's immediate. So I want you to write down the proof. So whenever I mention this why, you must go back, work on it, and then try to write a formal proof. Not just understand why. Try to write all these proofs as formal proofs. When you do your homework and things, always write it as formal because when you write in the exam, you have to write it formally in whatever happens, right? So it's a good idea to write formal proofs. Once you do this for, let's say, a couple of courses in graph theory, or at least the first course in graph theory, all the proofs you write formal, you can become a little informal later, right? And then try to see, try to put down the main ideas, because otherwise you might miss so many things. So it is very important that you write formal proofs and try to give reason for each statement that you make. And I expect your proof to be like that. Okay, so I have already given a couple of proofs which are formal. I will give some few more very important proofs. I will give formal proofs here in the class itself. But all the other proofs I will just describe to you sometimes or ask you to write the proof, right? So when I orally describe, you can take the notes and try to write your own proof later. But it is important that you do it, and I expect you to do it. So another proposition is that every non-trivial tree must contain a vertex of degree 1. Again, this is very easy to see from something that we proved earlier, right? Because we said that any graph with minimum degree, at least 2, contains a cycle, right? And therefore, because we are talking about acyclic graphs, that cannot be true, right? So that is already the proof. But try to write your own proof. Maybe you can find another proof. Then a degree of vertex, degree of a vertex is 1. Then such vertices in a tree are called leaves, right? So you have trees, and you are already saying that every tree has at least 1 leaf. But you can prove something stronger, that every tree has at least 2 leaves. How do you prove that? So every non-trivial tree has at least 2 leaves. Okay, of course, trivial tree has no leaves, and every non-trivial tree has at least 2 leaves. So how do you prove this? So there are several ways to prove this, but the easiest one I can think of is that that because it is non-trivial, there is at least 2 vertices, and by definition a tree is connected, so there is a path between any 2 vertices. So take the maximum length path in this graph, right? The tree that you are considering, look at any maximum length path, right? Now, if you take the maximum length path, right? Tree is a maximum length path. Then I claim that the endpoints of this path must be leaves, because this endpoint is not a leaf, that it has at least one more neighbor, right? And this other neighbor cannot belong anywhere other than the path itself, because if it is, if it has a neighbor which is outside this path, then I get a longer path in the graph, right? So this path becomes longer. So therefore, all the neighbors of the endpoint must belong to the path itself. But now, which means that you have 2 vertices in this path which are not adjacent, right? And this edge together with this path forms a cycle by definition of the cycle, and which is not allowed in our acyclic graph. So therefore, every non-trivial tree has at least 2 leaves, right? Endpoints, both of them are going to be leaves. That's it. So that is the proof. The proof I gave you is formal, but you have to just write it formally. Now another theorem is that if you have a graph which is a tree, then the number of edges is actually equal to the number of vertices minus 1. Again, many different ways to prove this. You can try to find your own proof, but I will give you one proof now. So let us start with a tree on, let's say, n vertices, right? Let the number of vertices be equal to n. So I start with an empty graph on n vertices. Okay. So empty graph on n vertices, which has exactly n components, right? Now the tree is connected, therefore it has only one component. Now we already proved that if you take 2 different components and add an edge between them, right? So two distinct components and add an edge, they combine to form one component, and therefore the number of components decreases by exactly one, right? So every time I add a edge to the graph, if it is between two different components, it decreases the number of components by exactly one, right? But then, suppose you add edges to vertices within the same components, then we know that it creates a cycle. This is also something that we either proved or I gave as a homework. I don't remember one. In either case, if we have not done, you can do it as a homework, right? So adding an edge between non-adjacent vertices of a right the same component creates a cycle, right? And because of that, we cannot do that, right? So every time if I add an edge, that edge must be between two different components of the graph, right? Now, which means that every time I add an edge to form a tree, it is going to decrease the number of components by exactly one. And I start with n components. So when it becomes n minus 1 edges, the number of components becomes exactly 1. So by adding n minus 1 edges, the graph becomes connected and it is acyclic, and therefore it forms a tree, right? So now every tree, right, it basically, like if you remove the edges, it becomes the empty graph. So I can put back the edges in this particular fashion, right? And every time I add an edge, it connects to different components. And therefore, what I get is going to be a graph with exactly n minus 1 edge, right? So this is one way. There are several different rules you can think about. You can use induction. You can use I mean, here we are using induction, of course, but there are many other ways to do this. Okay, think of your own proof and try to write, and do that. Here is another theorem. If T is a tree, then the vertices of the tree T can be enumerated. Then you can put it into an order, right? Let's say V1 to Vn, such that for I greater than or equal to 2, the vertex Vi has a unique neighbor in the previous vertices, that is V1 to Vi minus 1. Now this is also kind of easy to prove because we already proved that every tree contains some leaf, right? Now if you look at a leaf, removing a leaf, what can you say about the remaining graph? If I remove a leaf, the remaining graph will still be connected because the leaf is only having one neighbor, right? So no path between vertices can pass through a leaf, right? So except for that particular vertex, right? So therefore, there is no path which goes through this leaf because it has degree 1. And therefore, if I remove that leaf vertex, the connection between any other vertices is not disrupted. So I remove one leaf, I get a remaining tree. It will have another leaf if it is non-trivial. So therefore, I can keep on removing leaves from the graph, right? So if I keep on removing leaves, I will get a another vertices. So I start from the first leaf, name it as Vn, remove the leaf, I get remaining graph. Find another leaf, again remove it, call it Vn minus 1, right? And do it like this. And similarly, finally you will get B2 V1, which is an edge, and then you can do the you can trace back, right? So V1 to this one, and one can verify, right? You have to do this. You have to write it formally, write it that once I go back in this order, it is always going to be having this property, right? It has exactly a unique neighbor in the previous subgraph. Okay.